All right, lesson 2.2, simplifying radical expressions. We worked on simplifying radical expressions a little bit in grade 10, and over here on the right-hand side, I did an example for you. For instance, like if we had the square root of 8, we could simplify it by saying that we know that there's a perfect square root 4 inside of 8, so we could write it as root 4 times 2, and then simplify the square root of 4 is 2, so we get an answer of 2 root 2. So we've done a little bit of this before, and we're just going to extend with this lesson. All right. So if we have some root n of ab, we can say that that's also equal to some root n of a times some root n of b. All right. So for instance, that could be, when I'm saying some root, that could be square root, cube root, fourth root, whatever. A couple stipulations. What we must say is where n is a member of the natural numbers. Okay, so n must be 1, 2, 3, 4, 5, can't be anything else, and such that a and b are members of the real numbers. Okay, this property is used to write radicals in different forms. What we see is the term in front of an integer is called a coefficient. So for instance, when we dealt with coefficients in the past, we might say, let's say, something like 2x. All right. Well, the 2 is the coefficient. When we have radicals, you could have something like we have up there, where 2 root 2, and the 2 is the coefficient right there. Okay. Just to remind you, because we're going to be using some of this vocabulary, n is going to be your index, and k is going to be your radicand. Basically, whatever on the outside there is your index. Inside on here is your radicand. All right. A similar question that you would have seen in grade 10. Actually, I say this is a grade 10 question, just kind of a little bit of a review for you, is to arrange in order from least to greatest. Now, I'm going to assume that for a question like this, you don't have a calculator, so you can't just chuck it into your calculator and figure out what the decimal representation is. So therefore, what we would do for this is we would change to entire radicals. For instance, 5 root 2, we might change this one to be, well, we know that the 5 has been popped out of the radical. So inside the 5 was the square, or sorry, what 5 squared is, which is 25. So I could write that as 25 times 2, which gives you root 50. So I hope you understand how I got that, because we know that 5 inside of here would be 25, because when you take the square root of 25, you get 5. Okay, let's deal with this one. We would say that the 2 on the inside would be a 4, so we have 4 times 5 will give you root 20. And lastly, 4 root 3, the 4 on the inside was a 16, and 16 times 3 is 48. So if we wanted to put those in order from least to greatest, the least would be 2 root 5, next one would be 4 root 3, and the one after that would be 5 root 2. Okay. Let's take a look at one with some cube root action. Well, if you look at this carefully, you may have started to do the same thing that I just did, but you can avoid all that work. All right. So since each mixed radical is a multiple of the cube root of 2, all you need to do is compare the coefficients. If I highlight this, we all know that that is the same as that is the same as that. So therefore, the 8 must be the smallest, then the 9, then the 11 being the biggest. So in order, this is 8, the cube root of 2, 9, the cube root of 2, and 11, the cube root of 2. Simple. Okay. And C. C is kind of the best of both worlds. It combines a little bit of everything. We have something raised to the fourth root, something to the square, the square root, and something to the cube root. Well, this one's a little bit nasty because they're all different roots. If you ever get one like this, this would be one where I know I told you that you might not have been able to use a calculator for example 1. You would be able to use a calculator for this one. So since the mixed radicals have different indices, the indexes there, and there, you use a calculator. Okay, and so I'd like you to try to put those into your calculator. This will be some good experience for you to make sure this works okay. I'll give you a little bit of a hint here about how this goes. Let's do this first one. 3. Okay, and then if you want the 4th root of something, I'll give you a little hint. It's probably the easiest way to do this. If you remember, something to the 4th root is the same thing as just taking it and taking that 8 and raising it to the power of 1 over 4. That's an easy way to deal with big numbers. Okay, and so what we can do is we can say that this one was equal to 5.0453. 4 root 2, that one's easy to do on your calculator. 4 root 2. Oops. There we go, that's better. And we get 5.6568. I'm going to 4 decimal places. It doesn't really matter so long as you go enough that you can differentiate between these. And the cube root, 3 cube root of 5. I do have a cube root button, but I'm just going to do the same way I did the first one there. So I'll do 3, and then brackets, put the 5 in, and like I said, I'll raise it to the power of 1/3. Okay, if you have that cube root button on your calculator, feel free to use it if you find that easier. We get 5.1299, so we'd say that, which one was the smallest? The first one, I think. 3, 4th root of 8, and then it was 3, the cube root of 5, and lastly 4 root 2. Okay. In addition to the multiplication property of radicals, we have the division property of radicals. Alright, so what I'm trying to make reference of is, just like we had this property at the beginning, we have really the same one to deal with division, and it's what you'd expect. If we have sum root n, and then we have a divided by b inside that, we can divvy this up, and we can say it's sum root n of a, all divided by sum root n of b. Alright, a couple stipulations we have to say. Again, where n is a member of the natural numbers, and a and b are members of the reals. And another thing we have to say is that b cannot equal 0, because we cannot have 0 in our fraction right there. Dividing by 0, if you recall, that's illegal in math. We will spontaneously combust. Okay, so just a very brief example right there. I know it doesn't say I need to do one, but if I take the square root of 4 over 9, okay, well, if you were to put this into your calculator, you get, well, I'll show you. You get 0.6666, which essentially is 2/3. Okay. Now, if you break this up, you could write this as the square root of 4 all over the square root of 9. And of course, we know the square root of 4 is 2, and the square root of 9 is 3. So just showing you kind of how that rule works. It makes sense, not too crazy. So let's try an example simplifying one like so. We have the cube root of negative 16. So we can divvy this one up and say that we have the cube root of negative 16, all divided by the cube root of 135. I don't necessarily need you to do this additional step, but if you like to, that's fine. This next step you definitely would have to do. Now I want you to think of what are perfect cubes that go into negative 16. Well, one perfect cube that I know of that goes into that would be negative 8. Okay, a perfect cube that goes into 135 that I know of is 27. So that would be 27 times 5. Okay. Now simplifying that, the reason you can't, or the reason I took the negative out is because you actually can take the cube root of a negative number. If you take a negative and multiply by itself once and then twice, but for the 3 times, it will still be negative. So the cube root of negative 8 is negative 2. The cube root of 2 all over. The cube root of 27 is 3, so we have 3, the cube root of 5. Now, I would accept that as an answer. That is fine. You can go one step further if you wish. You could write this as negative 2 over 3, and then all under one radical, you'd write this as the cube root of 2/5. Either one of those that I have in a box right there would be fine. Okay. Alright, for this next question here, we're kind of going backwards. We want to write this as an entire radical. The one thing I want you to maybe focus in on a little bit is this negative out in front, because that could change some things. So let's take a look. If we have negative 3, the 4th root of 2 over 27, we want to write it as an entire radical, we got to take this and put it inside. Okay. Now, what we can do right here is we are actually just going to take the 3 and put it inside. The negative is just going to stay out in front. All right. So, for instance, if we have 3 and we took the 4th root, that means if you multiply 3 by itself 4 times, then it can go inside the radical. So I'm going to have, whoops, that's something that looks like this with the negative out in front. It's going to be something out of 27 times the 2. Well, what is that 3 inside the radical? Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. So we have now negative the 4th root of 162 out of 27. Now, if you check this in your calculator, if we take 162 and we divide by 27, that can be simplified further, such that we have negative the 4th root of 6. If you were to put this and that into your calculator, you would find out that those are exactly the same thing. They are equivalent. Good. Okay, moving on. All square numbers are greater than or equal to 0. So what we know is that the expression, the square root of x, has a real number value only when x is greater than or equal to 0. That is, the square root of x is defined only when x is greater than, sorry, not that is, the square root of x is defined for x is a member of the reals and x is greater than or equal to 0. Alright, so we're going to use this rule to help us in a second. It also has a cube root rule. So we had to square number 1, now we can deal with the cube roots. A cube root of a positive number is positive. The cube root of a negative number is negative. So we dealt with one before. For instance, the cube root of a negative 8 was negative 2. And we can go the third step and say the cube root of 0 is, of course, 0. So the expression, the cube root of x, has a real number value for all values of x. That is, the cube root of x is defined when for x is a member of the reals. So the difference between these two is when we have square numbers, we know that they have to be positive. For these ones, they can possibly be positive or negative. Example 3. For which values of the variable is each radical defined? Note what this question is saying. It's not saying simplify or anything. It just wants to know what possible values for x can we have. You're definitely going to have some of these in your assignment. Well, since we know that whenever you square a number, what happens to it? Well, even if you take a negative number or a positive number, it must become positive. So I can say that x squared must be greater than or equal to 0. All right. So therefore, x is a member of the reals. X can be anything. That is what that means. X can be anything. Let me show you what I mean. If I take any number and put it in here for x, doesn't matter, negative, positive, decimals, whatever you want, put it in there and square, it will become positive. Then if you take a positive number and multiply it by this positive 27, you can take the square root of anything that's positive, so you know that we are good to go. Okay, let's try B. This one's getting a little bit more difficult. So, we have the 4th root of negative 12x cubed. Well, what do we know about when we have x cubed? Well, we know that we could get something that is either positive or negative. Okay, so keep that in mind. Depending on what value we put in for x, it can become positive or negative. But we already have a negative here. All right. So, since the 4th root is defined only when the radicand, that's what's underneath the radical sign, is greater than or equal to 0, and the coefficient is negative, your solution for this one must be x is less than or equal to 0. And I'll talk to you about kind of why that's the case. Now, keep in mind, imagine that we just went with a positive number here. That would mean that we would